It is July 4, 2016. A spacecraft the size of a basketball court is hurtling toward the largest planet in the solar system at over 200,000 kilometers per hour. In minutes, it will fire its engine for half an hour to slow down enough to be captured by Jupiter's gravity. If the engine fires for 1 second too long or too short, the spacecraft misses the planet entirely and drifts into space forever. If it fires perfectly, it enters one of the most hostile radiation environments in the solar system, where the energy of a major solar storm is present every single day. The team at NASA's Jet Propulsion Laboratory sits in silence. There is nothing they can do. The signal from the spacecraft takes 48 minutes to reach Earth. By the time they hear whether the burn succeeded, it will already be over, one way or another. The burn succeeded. Juno entered Jupiter's orbit, and what it found there, over the next 9 years, overturned nearly everything we thought we knew about the largest planet in our solar system. We thought we knew Jupiter. For 4 centuries, since Galileo first turned a telescope toward it in 1610, humanity has been staring at this planet. We watched its storms, we photographed its moons, we sent spacecraft to orbit it, plunge into it and fly past it at tens of thousands of kilometers per hour. By the time NASA launched Juno in 2011, the scientific consensus was clear. Jupiter was big, it was violent, it was well studied, the fundamental questions had been asked. Most of them had been answered. Then Juno arrived, and within its first few passes, the answers started falling apart. Not minor adjustments, not small corrections to existing models, fundamental revisions, the kind that require scientists to go back to the beginning and rebuild from scratch. Everything from the nature of Jupiter's core to the depth of its storms to the mechanism driving its auroras turned out to be wrong. Not slightly wrong. Wrong in ways nobody expected, and most people have never heard about any of it. Let us start at the center, because this is where the first shock hit. Before Juno, the standard model of Jupiter's interior was this: a solid rocky core at the center, roughly 10 times Earth's mass, surrounded by a thick layer of liquid metallic hydrogen, the exotic state of matter that forms when pressure becomes so extreme that hydrogen atoms lose their electrons and conduct electricity like metal. Above that, a deep layer of ordinary liquid hydrogen and helium, transitioning gradually into the atmosphere we see from the outside. This model was not a guess. It was the product of decades of theoretical work. It was supported by every piece of data available. It made sense. It was elegant. It was wrong. Juno carries 2 instruments that changed everything. A microwave radiometer capable of measuring heat deep inside Jupiter's atmosphere, far below anything previous spacecraft had reached. And a gravity science experiment of extraordinary precision, measuring tiny variations in Jupiter's gravitational field as the spacecraft orbits. Those variations reveal how mass is distributed inside the planet. When scientists processed the data, they found something that had no place in any existing model. Jupiter does not have a small, compact, solid core. It has what researchers now call a fuzzy core. A diffuse, extended region of heavy elements with no sharp boundary, blending gradually into the surrounding layers, stretching outward to perhaps 40% of Jupiter's total radius. Not a ball, not a rocky center, a vast, hot, slowly churning mixture of rock and metal and hydrogen and helium that extends nearly halfway to the surface. The best explanation is a collision. Early in Jupiter's history, a protoplanet roughly 10 times Earth's mass may have slammed into Jupiter at enormous velocity. The impact shattered and dispersed the original compact core, mixing its material deep into the interior. 4.5 billion years later, that material has not separated back out. Jupiter is still carrying the wreckage of a collision that happened before the Earth existed. The fuzzy core is a scar, the oldest scar in the solar system, but the core was only the beginning. Before Juno, no spacecraft had ever directly measured what was happening deep inside Jupiter's atmosphere. The Galileo probe plunged in during 1995 and transmitted data for 57 minutes before the pressure crushed and vaporized it, but Galileo entered through an anomalously dry, calm region. Its data was useful, it was not representative. Juno's microwave radiometer was different. By measuring emissions at multiple frequencies, each one penetrating to a different depth, Juno built a three-dimensional map of Jupiter's weather that no instrument had ever produced before. What it found was not weather. Not in any sense we understood. Jupiter's atmospheric bands, the alternating light and dark stripes that wrap around the planet, are not shallow surface patterns. They extend downward for at least 3,000 kilometers below the visible cloud tops. That is deeper than the entire radius of the Earth. The jet streams that create those bands are not atmospheric currents skimming the surface of a calm interior. They are enormous columns of moving gas reaching thousands of kilometers into the planet. Jupiter's atmosphere is not a skin. It is a deep ocean of gas in constant violent motion, and the stripes we have been looking at for centuries are just the top layer of something far larger and far stranger underneath. Solar heating cannot explain this. The sun's energy becomes irrelevant at 3,000 kilometers depth. What is driving those jet streams is Jupiter's own internal heat. Jupiter radiates more energy into space than it receives from the sun. Its interior is still warm from the gravitational energy released when it formed, and that heat drives planet-wide convection that reaches from deep inside all the way to the clouds. The bands are not weather. They are the surface expression of a heat engine that has been running for 4.5 billion years. And then there was the Great Red Spot, the most famous storm in the solar system, continuously observed for at least 350 years, large enough to swallow the Earth. Before Juno, the assumption was that it was a surface feature, a massive but shallow atmospheric disturbance. Juno's radiometer settled that question. The Great Red Spot extends approximately 500 kilometers below the visible cloud tops. 500 kilometers, that is a storm with roots reaching into regions where the pressure is dozens of times greater than at Earth's surface. It is not sitting on top of the atmosphere, it is embedded in it. A column of churning gas, driven by both solar heating above and internal heat below, that has somehow maintained its structure against the shearing forces of the jet streams on either side for centuries. The mechanism that keeps it stable, at that depth, at that scale, is still not understood. Then came the poles. Before Juno, Jupiter's poles had never been clearly imaged. Previous spacecraft stayed near the equatorial plane. Juno's orbit took it directly over the poles on every pass, but before the images arrived, the magnetometer had already found something that shocked the team. Jupiter's magnetic field was known to be roughly 20,000 times stronger than Earth's. The assumption was that it was broadly dipolar, North Pole and South Pole, like an enormous bar magnet. Juno's magnetometer destroyed that assumption. The field is profoundly asymmetric, significantly stronger in the northern hemisphere than the southern. There is a region near the equator where the field reverses direction entirely, pointing inward rather than outward. This irregular, lopsided structure has no equivalent anywhere else we have studied. The explanation connects back to the interior. The liquid metallic hydrogen layer that generates the field does not extend to the same depth everywhere. Where it is shallower, the field is weaker. The asymmetry in the field is a map of asymmetry in the interior. Jupiter's inside varies in ways we are still trying to characterize, and that variation is written into every measurement of the magnetic field that any instrument will ever take. Then the pole images arrived, and when they did, scientists could not quite believe what they were seeing. Cyclones. Not one or two, dozens. Enormous geometric arrangements of cyclones, each one larger than the continental United States, packed so tightly their edges touched. At the North Pole, a central cyclone surrounded by 8 others in a perfect octagonal arrangement. At the South Pole, a central cyclone surrounded by 5. These patterns have persisted, unchanged for years. On Earth, Cyclones merge when they get close. They collide, one absorbs the other, the system reorganizes. The cyclones at Jupiter's poles should merge. They are touching. They do not. They hold their geometric pattern year after year, in a configuration that no model of fluid dynamics can currently explain. As of 2025, the stability of Jupiter's polar cyclone systems remains one of the genuinely open, unsolved problems in planetary science. And from those same poles came the lightning. Jupiter's lightning was detected by Voyager in 1979, but only as faint radio signals. Juno measured it directly. What it found overturned another assumption. Scientists had expected Jupiter's lightning to be concentrated near the equator, where solar heating is strongest and convection is most active. Instead, lightning clusters near the poles. It originates from water clouds at a specific altitude, roughly 50 to 65 kilometers below the cloud tops, where temperatures remain warm enough for liquid water to exist, despite the extreme cold higher up. That distribution is a map. Every bolt marks a location where liquid water exists, where convection is carrying heat upward from the interior, where Jupiter's internal engine is doing its work. The lightning is not a hazard, it is a diagnostic tool, a way of reading Jupiter's interior from the outside. Then came the auroras, and this is where it gets genuinely strange. On Earth, auroras are powered by the solar wind. Charged particles from the sun follow magnetic field lines into the atmosphere and produce light. Scientists assumed Jupiter's auroras worked the same way, just larger and more intense. Juno measured them from inside the magnetic field. The answer was different. Jupiter's auroras are not primarily powered by the solar wind. They are powered by Io. The most volcanically active body in the solar system constantly erupts material into space. That material gets ionized by Jupiter's radiation environment, trapped in the magnetic field, and spirals toward the poles, generating electrical currents that drive the aurora. Io is the generator. Jupiter's atmosphere is the bulb. The power flowing through this system is roughly 100 times greater than all of Earth's auroras combined. It is a planetary electrical circuit, and Io is what keeps it running. The final major discovery involves water, and it is still unresolved. One of Juno's primary objectives was to measure how much water exists in Jupiter's atmosphere. Water abundance reveals where Jupiter formed in the early solar system. The Galileo probe had found very little, but it entered through an anomalously dry region. Juno was designed to get a global answer. What it found was that water abundance varies dramatically across latitudes and altitudes. More water near the equator, more water deeper in the atmosphere. Jupiter's water is not evenly mixed. It is layered and redistributed by complex weather systems operating across thousands of kilometers of depth. The full implications are still being worked out, but the heterogeneous distribution complicates every existing theory of how and where Jupiter formed. In 2021, NASA extended Juno's mission. Instead of deorbiting, the spacecraft was redirected to fly past Jupiter's moons. It passed Ganymede, Europa, and Io. The Io flybys in late 2023 and early 2024 brought Juno closer to that moon than any spacecraft since Galileo. The images showed volcanic plumes erupting in real time, lava lakes kilometers across, surface features that simply did not exist in Galileo's maps from 20 years earlier. Io had been resurfaced, mountains had formed where none had been. Lava fields had buried older terrain entirely. The most volcanically active body in the solar system is not just active, it is being continuously remade. Nothing on its surface stays the same for long. Juno is still up there, still orbiting, still transmitting, but the radiation has been steadily damaging its instruments since the day it arrived, and its orbit is slowly decaying. Eventually it will deorbit into Jupiter and be crushed and vaporized, just like Galileo before it. Before that happens, every remaining orbit is another dataset, another set of measurements that scientists will spend years extracting meaning from. There is one more thing Juno changed about our picture of Jupiter. Not what it found, but what it reopened. The standard theory of Jupiter's formation is called core accretion. A solid rocky core forms first. Then, once it reaches a critical mass, it begins pulling in gas from the surrounding protoplanetary disk. The gas builds up until you have a gas giant. The fuzzy core challenges this model directly. If Jupiter's original compact core was shattered by a collision, the signature of that compact core is gone. What remains is a mixed, diffuse region that looks nothing like what core accretion predicts. Some scientists now argue that Jupiter may have formed through a completely different process, direct gravitational collapse of a gas cloud with no distinct rocky core phase at all. Others argue the collision model can be reconciled with core accretion if the timing is right. The debate is ongoing, but Juno's data has forced it open again, decades after most planetary scientists thought it was settled. And the water distribution adds another layer to this. Where Jupiter formed in the solar system determines how much water it should have incorporated. Closer to the Sun, less water. Further out, more. Juno's finding that water is not evenly distributed makes it difficult to extract a single formation distance from the data. Jupiter may have formed in a different location than it currently orbits. It may have migrated significantly inward during the early solar system, a possibility supported by other independent evidence. The water data does not contradict this, but it means we cannot yet use water abundance to pin down exactly where Jupiter began its life. The question remains open, and it is a question that matters because Jupiter's formation location determined how it shaped the entire inner solar system, including the conditions that eventually led to Earth. Here is what all of it means taken together. The fuzzy core, the 3,000-kilometer jet streams, the 500-kilometer storm routes, the polar cyclones that should not be stable but are, the asymmetric magnetic field, the moon-powered aurora, the heterogeneous water distribution. Every single one of these was a surprise. Every single one required a revision to models that had been considered settled. Jupiter is not what we thought it was. Not the interior, not the atmosphere, not the magnetic field, not the storms, and that matters beyond Jupiter. Gas giants are the most common type of planet found around other stars. The models used to understand those distant worlds were built on assumptions about Jupiter that Juno has shown to be wrong. Every revision ripples outward. One spacecraft, one planet, and the implications go everywhere. For 4 centuries we studied Jupiter at a distance. We built models from what we could observe at the cloud tops. Those models were the best we could build with what we had, and they were wrong about almost everything below the surface. We did not know we were wrong because we had no way to check. Juno went deeper, and when it did, the map changed. That is not a failure. That is exactly how science is supposed to work. Jupiter has been here for 4.5 billion years. It was here before the Earth formed. It shaped this solar system in ways we are still uncovering, and after everything we have pointed at it, it is still surprising us, still overturning assumptions, still being, in every encounter, something stranger than we expected. If you enjoyed this video, consider subscribing. I will see you in the next one.